In this tutorial, I am going to discuss a sample problem on charge distribution and a conducting sphere. Welcome to this episode of Physics is Easy with Mr. Jesse. Suppose the conducting spherical shell in the figure below carries a charge of 3.2 nanocoulomb and that a charge of negative 2.20 nanocoulomb is at the center of the sphere. What is the charge distribution on the inner surface of the sphere and B on the outer surface of the sphere? So let us visualize our problem. This charge of 3.20 nanocoulomb is the charge of the sphere, and in fact it is this capital Q, so that's 3.20 nanocoulomb. And a charge of negative 2.20 nanocoulomb is at the center of a sphere, so therefore this small q here is negative 2.20 nanocoulomb. So our sphere here has two surfaces. We have the inner surface and we also have the outer surface. And these surfaces have different charge distribution. So in order for us to solve for the charge distribution in the inner surface, let us consider this charge that is inside our sphere. Now this charge, which is negatively charge, by the way, would have electric fields pointing inwards, and therefore there is an electric field that goes from up towards the charge. There is also that electric field here. So this electric field points in all direction. Now since this electric field is pointing downward, it cancels with the electric field that points upward. There would also be an electric field that points towards the right and an electric field that points towards the left, and this electric field is going to cancel. There is another electric field here and it cancels with the electric field there. So as a matter of fact, the electric field that is pointing in all direction would actually cancel each other. And if we define electric flux as electric field times area, and this electric field actually cancels in all directions, then we could say that the net electric flux is actually equal to 0. And according to Gauss's law, electric flux is equal to Q enclosed or Q inside the Gaussian surface divided by permittivity. Now, if the electric flux is equal to 0, so that's our electric flux, then we have to know what is inside our Gaussian surface, or the charge inside our Gaussian surface that would give rise to a zero electric field. So inside our Gaussian surface, we actually have, so our Q inside, as a matter of fact, Q inside would be equal to the charge at the center plus the charge in the inner surface. So the charge in the inner surface, let me write that as QI. Charge in the inner surface, where QI, we write that down. Charge of the inner surface. Inner surface. So if our Q inside, if our Q inside is 0, because this is the only reason that your electric flux is going to be 0, that means your Q inside the Gaussian surface should be 0, then we will have our Q at the center, which is negative 2.20 nanocoulomb, plus QI, or the charge of the inner surface. Then we will have QI is equal to positive 2.20 nanocoulomb. 2.20 nanocoulomb. Positive 2.20 nanocoulomb. That is the charge of the inner surface. So in fact, our answer for A is 2.20 nanocoulomb. So in fact, the charge of the inner surface is actually just equal to the negative of the charge that is in the center of the sphere. So take note of this statement. Now moving on to part B, the charge on the outer surface of the sphere. So we know, we are now solving part B. This one here is part A. This is part A. We are now solving for part B. Now we know that the overall charge of the sphere, which is capital Q, is equal to 3.20 nanocoulomb. And this overall charge, which is Q, is composed of the charge in the outer shell or outer surface plus the charge of the inner surface. So if we are going to use that equation, or if we're going to use that analysis, our overall charge, which is 3.20 nanocoulomb, is equal to the charge of the outer surface plus the charge of the inner surface, which we have solved to be 2.20 nanocoulomb. Then we could manipulate this equation to come up with the charge of the outer surface. That would be equal to 3.20 nanocoulomb minus 2.20 nanocoulomb. Therefore, the charge of the outer surface is equal to 1.0 nanocoulomb. And in fact, remember that the overall charge of our shell is just equal to the charge of the outer surface plus the charge of the inner surface. And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.